Welcome to TechNova Podcast. Okay, welcome to the deep dive. Today we are jumping headfirst into something really central to the AI explosion happening right now, the hardware race. Specifically, we're looking at a pretty big announcement from AMD. It's about their latest AI GPUs, the Instinct MI350X and the MI355X.
That's right. And our source for this deep dive is a really detailed article from Tom's Hardware. It breaks down the specs, the architecture changes, and maybe most importantly, the performance numbers AMD is throwing around for these new chips.
Yeah, and our mission here is to, cut through some of the hype. We want to understand what these chips actually are, what kind of performance gains AMD is really claiming. And believe me, some of the numbers are, well, they're big.
They really are.
We'll dig into the tech behind them and then try to figure out what this all means for that really intense competition going on in AI hardware.
Yeah, the article definitely teases the potential. AMD is claiming some pretty eye-popping generational gains compared to their own previous chips, right?
Right.
We're talking up to 4x in what they call AI compute performance, and this is the one that really jumps out, up to a 35x speedup specifically for inference tasks.
Okay, wait. 35x faster inference, just generation over generation?
That's the claim.
Wow, that definitely gets your attention. And they're not just comparing against older AMD stuff, right? They're putting these up against Nvidia.
Exactly. They're claiming competitive performance, even leading in some specific benchmarks against rivals like Nvidia's latest.
Yeah.
So, yeah, big claims all around.
Okay, let's unpack this then. What exactly are these two chips, the MI350X and the MI355X?
So these are AMD's newest additions to the Instinct family. They're built, squarely for heavy-duty AI workloads. They training massive models, running inference really fast. And they're based on AMD's brand new CDNA 4 architecture. That's their GPU design, specifically tailored for data centers and high-performance computing.
Got it. CDNA 4. And the source said they share, the same basic silicon design. So how are they different?
Exactly. The underlying chip design is identical. The main difference, and it's the really practical one for data centers, comes down to cooling and power.
Okay.
So the MI350X, that one's geared towards your more traditional air-cooled server racks.
Yeah.
It runs at a somewhat lower total board power, or TBP.
Makes sense. And the MI355X, that must be the other side of the coin.
Right. That's the one designed for liquid-cooled systems. And because liquid cooling is way more efficient at getting heat out, it lets them push the power consumption way up.
How high are we talking?
Up to 1,400 watts, according to the article, which is, well, pretty staggering for one board. But it lets them extract the absolute maximum performance.
1,400 watts. Okay, that's a serious commitment. What about the features they have in common?
Both are absolutely loaded with memory, which you need for these huge AI models, right?
Definitely.
They pack up to 288 gigabytes of the latest HBM3E memory, and that gives them just enormous memory bandwidth, up to 8 terabytes per second.
8 terabytes a second. Wow.
Yeah. And another really key update the article highlights is native hardware support for these newer, lower precision data types, specifically SP4 and FP6.
Okay, FP4 and FP6. Why are those lower precision formats becoming so important for AI?
That's where a lot of the speed gains, especially in inference, are coming from. When you run calculations using fewer bits, lower precision.
Less data to move.
Exactly. Less data to move. And the calculations themselves can often be done much, much faster, especially for tasks like inference, using a trained model to generate text or answer questions.
Right. Makes sense. And the article mentioned a change from the previous generation, the MI300A.
Yeah, good point. The MI300A was actually different. It was an APU. It had both CPU and GPU cores fused together on one package.
Right, an accelerated processing unit.
Exactly. These new chips, the MI350X and MI355X, they're pure GPUs. All that silicon real estate, all that power budget, is focused just on the massively parallel compute that AI workloads demand.
Okay, so pure GPU focus. Let's get back to those performance numbers. AMD is making some pretty bold claims. What are the specifics from the source?
Okay, so compared to their own last-gen MI300X,
Yeah.
they're hitting those headline figures we mentioned, up to 4x improvement in overall AI compute, and that really massive 35x jump, specifically in inference performance.
35x, it's still kind of hard to wrap your head around.
It is. They also mentioned an overall performance uplift of up to 3x across more general workloads compared to the MI300X.
Those are aggressive numbers. What's the technical magic behind gains like that? How are they pulling it off?
Well, the source points to two main drivers here. First is that jump to the new CDNA 4 architecture we talk about.
Right.
That brings architectural improvements, doing more work per clock cycle, better efficiency specifically for AI math.
Okay, architecture first, what's second?
Second, and this is really crucial, is the manufacturing process for the core compute chiplets, the bits doing the actual math, which AMD calls XCDs.
Yeah.
They've moved to a more advanced process node. They're using TSMC's N3P process for those compute dies.
N3P. And a smaller node usually means you can cram more transistors in, right? Better density.
Precisely. The article states the total transistor count is now 185 billion on these chips.
185 billion. Wow, how does that compare?
It's a big jump. About a 21% increase over the 153 billion transistors in the previous generation, and more transistors built on a more advanced, more efficient process. Well, that translates directly to more potential compute power.
The article also brought up something about performance and different precisions, like not everything got faster across the board, mentioned FT64.
Yeah, that was an interesting nuance. While the lower precisions like the FP4 and FP6 we mentioned see these huge gains that are great for inference.
Right.
The article notes that FP64 matrix performance, which is important for some traditional scientific computing, is actually halved compared to the MI300X.
Halved, okay.
But FP64 vector performance is stable. So it suggests AMD is really optimizing the design for where the bulk of the AI market is going, which is mixed precision training and especially low precision inference.
And they made a point about FP6 running at FP4 speeds.
Yeah, they highlighted that. They see it as a potential advantage, being able to run FP6 precision workloads essentially as fast as FP4.
Yeah.
Gives users a bit more flexibility, maybe better accuracy than FP4, but with similar speed.
Okay, let's peel back the cover a bit more. The physical construction. How are these chips actually built? The source mentioned advanced packaging.
Oh yeah, this is where things get really sophisticated. AMD is using a combination of 3D and 2.5D packaging techniques. It's quite complex.
3D and 2.5D. Can you break that down a bit?
Sure. Think of 3D packaging like stacking things vertically. They actually fuse the accelerator compute dies, the XCDs, directly on top of the I/O dies, the IODs, like layering building blocks.
Okay, stacking compute on I/O.
All right. Then 2.5D packaging is used to connect these stack units horizontally. They place these combined stacks side by side on a larger piece of silicon called an interposer. And that interposer connects them to each other and also connects them out to the stacks of HBM3E memory.
So stacking up the core brain bits, the compute, and then wiring everything together horizontally on a base layer.
That's a pretty good way to picture it, yeah. The structure uses 8 of those compute chiplets, the XCDs. Each one has 32 compute units enabled, so that totals up to 256 CUs for the whole GPU.
And you mentioned I/O dies, the IODs. What's their role?
Yeah, they're like the central traffic controllers. They handle all the communication, getting data in and out, managing things. They actually stayed on the slightly older N6 manufacturing node.
Okay.
But AMD made a clever change here. They reduced the number of IOD tiles from 4 in the previous generation down to just 2. The article suggests this simplifies the overall chip design.
Simplifying is usually good, but what's the actual performance benefit of going from 4 IOD tiles down to 2?
This is a key point the source really emphasizes. By consolidating the IOD, AMD managed to significantly improve the internal communication pathways on the chip.
How so?
They doubled the width of the Infinity Fabric bus, that's the super fast highway connecting different parts of the chip together.
Yeah.
This boosts the bisectional bandwidth, meaning data moving across the chip in both directions simultaneously, up to a really impressive 5.5 terabytes per second. Just internally.
5.5 TB's internal bandwidth. Wow. How does that translate to better performance, though?
Well, besides just moving data faster internally, making that communication fabric more efficient allowed them to reduce the power consumption of the uncore parts of the chip, basically everything that's not the main compute engines.
Oh.
They could lower the frequency or voltage needed for that internal bus, and that freed up precious watts from the power budget.
So they can redirect that saved power to the compute chiplets.
Exactly. More power available for the XCDs means they can run faster, sustain higher clocks, and ultimately deliver more compute performance. It's a clever trade-off.
Makes sense. Where does the cache fit in? Infinity cache.
Right. The Infinity Cache acts as a fast buffer in front of main HBM3E memory. It helps speed up data access. The source says there's 32 megabytes of this cache associated with each stack of HBM memory.
And connecting this whole beast to the rest of the server, how does that work?
It uses a standard PCIe 5.0 by 16 interface. That's the main connection to the host system, the CPUs, the network cards, and so on.
Okay, standard PCI 5.
And what's neat is, despite being built from all these different chiplets, it presents itself to the operating system as just one single unified logical GPU. Makes software integration easier.
Gotcha. And for linking multiple GPUs together within the same server box.
So that really fast chip-to-chip communication, they use 7 dedicated Infinity Fabric links coming off each GPU. These links provide a total bandwidth of 1,075 gigabytes per second directly between the accelerators in a server node.
Okay, let's circle back to that power number. 1,400 watts for the liquid-cooled MI355X. You mentioned it's a big jump from the 750 watts of the MI300X, even the 1,000 watts of the intermediate MI325X. Why push power consumption quite that high? What's AMD's reasoning?
Yeah, it's a significant increase. According to the source, AMD's justification is all about performance density.
Density, meaning?
Packing more raw compute power into the same physical space, like a standard server rack. By allowing the individual chips to draw more power, they can deliver much higher performance per unit of volume.
And how does that help the customer, the data center operator?
Well, it ties into that metric everyone cares about, total cost of ownership, or TCO.
Right.
Even though a single chip uses more electricity, if you can fit, say, twice the compute performance into one rack because of that higher power per chip.
You might need fewer racks overall.
Exactly. You could potentially need fewer racks, less physical floor space, maybe less networking gear, less cooling infrastructure for the same total amount of AI processing power. So the cost per unit of performance when you look at the whole rack or even the whole data center could actually go down. That's the goal anyway.
Okay, I see the logic. The article also talked about the physical shapes, the form factors, and how these plug into servers.
Yes, both the MI350X and the MI355X use the OAM form factor. That stands for OCP Accelerator Module. It's an industry standard design for these high-power accelerator cards in data centers.
OAM. Okay.
And these OAM modules are designed to slot directly into standardized server-based boards, often called UBBs, or universal-based boards, which also follow the Open Compute Project OCP specifications.
And the advantage of using these standards?
AMD says it speeds up deployments significantly. Data centers are already familiar with these standards. The racks are designed for them. It makes integration faster and easier than dealing with lots of proprietary hardware designs.
Makes sense. And inside one of these standard server nodes, how do the, say, 8 GPUs typically talk to each other?
Within a single node, which often has 8 of these accelerators, they use what's called an all-to-all topology. Every GPU can talk directly to every other GPU.
Okay.
This is enabled by those high-speed Infinity Fabric links we discussed earlier. The source specifies 153.6 gigabits of bi-directional bandwidth between each pair of chips within the node.
And what's running the show? The CPUs.
Yeah, the source mentions these nodes are typically paired with 2 of AMD's latest 5th-generation EPYC server CPUs, codenamed Turin.
Got it. What about networking beyond a single server for building really big AI clusters?
Absolutely critical for large-scale AI. The article highlights support for advanced networking. For scale-out, connecting many nodes together, they mention support for NICs, network interface cards that are compliant with the Ultra Ethernet Consortium, or UEC.
Okay, Ultra Ethernet for scale-out.
And for scale-up, which is about creating even tighter connections between accelerators, sometimes across multiple nodes, they utilize something called the Ultra Accelerator Link, or UAL interconnect. These are specialized, high-bandwidth, low-latency links designed specifically for these massive AI and HPC clusters.
Okay, specialized interconnects. And we talked about air cooling versus liquid cooling affecting the chip's power. How does that play out at the full rack level? What do AMD's full rack solutions look like?
This is where you really see the density difference play out.
Yeah.
AMD offers full rack solutions based on the cooling method. The direct liquid cooling racks, the DLC ones.
For the MI355X.
Exactly, for the high-power MI355X. Because liquid cooling is so much better at removing heat, they can pack these racks incredibly densely. A single DLC rack can apparently hold up to 128 of the MI355X GPUs.
128 GPUs in one rack. Wow.
Yeah, and that totals up to a massive 36 terabytes of HBM3E memory just in that one cabinet.
That's incredible density. What about the air-cooled option for the MI350X?
Air cooling just can't handle that much heat load in the same space. So the air-cooled racks, designed for the MI350X, top out at 64 GPUs per rack.
Still a lot, but half the density.
Right. Half the GPU count, and consequently half the total HBM3E memory, 18 terabytes per air-cooled rack. So your choice of cooling directly impacts the maximum compute and memory density you can achieve per rack.
It really sounds like AMD isn't just selling chips anymore. They're pushing these complete integrated rack systems.
Absolutely. The source makes a point of emphasizing this strategic shift. AMD is focusing much more on delivering these as fully validated rack-scale solutions. They've made acquisitions, they're working closely with server partners, the OEMs.
Why the shift?
Because deploying AI at this scale is complex. Customers want solutions that are easier to deploy and manage. To really compete effectively against, well, primarily Nvidia's DGX systems and similar integrated offerings, AMD needs to provide that full-stack, rack-level solution, not just the individual components.
Makes sense. Okay, so we've got the chips, the tech specs, the architecture, the power story, the packaging, the rack systems. Let's get to the part everyone's waiting for, the benchmarks. How do these new AMD chips supposedly stack up against the competition based on what AMD shared in the article?
Right, the competitive landscape. This is always interesting, but like the source article wisely cautions, you always have to take vendor-provided benchmarks with a healthy grain of salt.
Sure, they pick the tests that make them look good.
Exactly. They control the configuration, the software stack, the specific workload.
Ugh.
But with that caveat in mind, AMD did present several comparisons, mostly pitting their new MI355X against Nvidia's B200 and GB200 platforms.
Okay, what did they claim for inference performance? That seemed like a big focus.
It was, particularly using that fast FP4 precision. AMD showed benchmarks where they claimed, for example, that a system with their MI355X could be 1.3 times faster than Nvidia's DGX GB200 system on certain tests using the large Llama 3.1 405 billion parameter model.
1.3x faster on Llama 405B. Okay, any others?
They also claimed a 1.2x speedup compared to an 8 GPU server using Nvidia's B200 chips when running inference on a model called DeepSeek R1. And in some other Llama 3.1 tests, they showed roughly equivalent performance to the Nvidia setups.
So claims of being faster in some cases, equivalent in others, specifically for inference. What about training these big models?
For training workloads, again comparing against Nvidia's B200 GB200-based systems, AMD's claims were more around being competitive or having maybe a slight edge in some scenarios. They highlighted about a 1.13x advantage in training performance on various Llama models.
Okay, competitive on training, potentially faster on inference. And going back to their own previous generation, that MI300X, did they give more specifics on where those big generational gains, like the 4X and 35X, actually come from, like for specific tasks?
Yes, they did provide some more detailed breakdowns for that MI355X versus MI300X comparison. For things like AI agents or chatbot applications, they claimed up to a 4.2x performance increase.
4.2x, okay.
For tasks like content generation, text summarization, conversational AI, those gains were stated as being in the range of 2.6x to 3.8x faster.
Still very significant.
Definitely. And they also cited specific model training improvements, like being 3 times faster generationally for training DeepSeek R1 and 3.3 times faster for training something called Llama 4 Maverick.
All right, so let's tie all this together. We've gone through the architecture, the power, the packaging, these benchmark claims. Connecting this back to you, the listener, why should you really care about the nitty-gritty details of the MI350X and MI355X?
Yeah, that's the crucial question, isn't it? Why does this matter to you? Well, these chips and others like them, they are quite literally the engines powering the AI tools and services that you're probably interacting with more and more.
Like chatbots, image generator.
Exactly. The speed and sophistication of the latest chatbot answered your question, how quickly AI can generate an image or summarize a long document, how fast complex data analysis gets done in the cloud. It all comes down to the power of the underlying hardware, the silicon, like this. So when AMD or Nvidia or Intel make these kinds of leaps in performance, it means that companies building and running these AI services can do things faster, they can potentially train and deploy even larger, more capable models, or maybe they can offer these services at a lower cost because the hardware is more efficient.
So it directly impacts the AI experiences we have.
Absolutely. This deep dive really just highlights the incredible pace of innovation and the really fierce competition that's driving AI capabilities forward at lightning speed. It's the engine room getting a massive upgrade, constantly getting faster, more powerful, more efficient.
It really underscores how rapidly the very foundation of AI is shifting under our feet.
It's relentless. A constant push for more performance, more memory, higher density, all while trying to manage that exploding power consumption.
Okay, so to quickly recap our deep dive, based on that Tom's Hardware article, AMD is making a pretty significant play with these new Instinct MI350X and MI355X GPUs. They're using a new architecture, CDNA 4, and advanced chip manufacturing to claim some really substantial generational gains, especially that huge jump in inference speed.
Right. And they're positioning themselves aggressively against competitors like Nvidia, showing benchmarks claiming parity or even advantages in certain areas. And importantly, they're not just selling chips. They're building out these full high-density rack-scale solutions, particularly with that liquid-cooled MI355X, really pushing the limits on power and performance density.
And as we see chips like these continue to push the absolute boundaries of performance, but also power draw for AI, it leaves us with a pretty big question to chew on, doesn't it?
It does. What are the broader implications of this trajectory? What does it mean for the infrastructure needed to actually support this explosive growth? We're talking about immense energy demands, the need for ever more sophisticated cooling systems in data centers, and maybe even a greater concentration of this immense computing power.
What does that future look like when this kind of AI processing power becomes even more widespread, even more accessible? What new possibilities open up and what new challenges arise?
Definitely something to think about.
Plenty to consider. Thanks for joining us for this deep dive.